Okay, nice. Huh. So today we'll be talking about counting. It's like one of the most fundamental things. Um, let's try to count some things. Like first, okay, there are two main things I want to start off with. Let's try to look at some examples and derive some things from them. So let's say I give you three numbers. Let's say 1, 2, and 3. How many three-digit numbers can you make out of these?
6 numbers.
6. Does everybody agree? Does somebody have a different answer? I also kind of just tricked you, so it's not 6. I mean, there's like something you need to still confirm. So I didn't clarify whether the numbers are allowed to repeat or not. So let's all just solve both the problems. So let's say repetition is allowed. You're allowed to repeat the numbers. Then how many numbers can you form? Is that
Uh,
is that answer
27.
6 or
27.
27? Okay, and wow, how did you find it this fast? That was very fast. Did you like write down all the 27 numbers or something?
Yeah, I write down all the 27 numbers.
Insane speed, bro. Damn, crazy. So yeah, I like maybe somebody can speak up and say what the thing is. Yeah. So how do you get to 27?
Because in there are three options and there is no repetition. So the way to fill first is 3, and second one also 3, and third one also 3. So 27.
Yeah, yeah. There's like a lot of different ways to think about this. But they all like boil down to the same thing. The first one, you can either have a 1 or a 2 or a 3. And if it's a 1, then you can have again three options. You can either have a 1 or a 2 or a 3. Again, if it's a 2, you have three options. You can either have 1 or a 2 or a 3. If it's a 3, you have three options. So this gives us some numbers. Now, in each of these cases, again, you're going to get three more cases for the last thing. So in total, what you're going to get is first you have like these three. Then for if you consider the first digit and the second digit, you're going to get 3 times 3, which is 9. And if you consider then if you consider the options for the last digit as well, for each of these 9 two-digit numbers, you're going to have three more. You're going to have three-digit numbers corresponding to it. So you get 9 times 3, it is 27. Does this make sense to everyone? This is basically what we are going to be doing over and over in class today. Does it make sense as to why it's not 3 plus 3 plus 3 and why it's 3 times 3 times 3? Yeah, okay. So over here repetition was allowed. You were allowed to repeat. Let's say you're not allowed to repeat now. So you can only once you write a 1, you can't write another one again. So how will that work? So the answer for this, I believe some of you guys already said it is 6. So how do we come to this answer? We can just pull an emon and write down all of them. So like you can just say 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 3, 1, 3, 1, 2, 3, 2, 1. Do them all in ascending order. There do seem to be six. Uh, yeah. You want to find out how many three-digit numbers there are, which only use the digits 1, 2, and 3, and you're not allowed to repeat the same digit twice. So, do you get this? And yeah, okay, so you list down all of them as six. What if I ask you the answer for five? How many five-digit numbers are there using the digits 1, 2, 3, 4, 5? And you're not allowed to repeat. Oh, don't put it in the chat. It's so hard to follow the chat. Can you unmute and say?
120 numbers.
For 5 digit, it will be 120.
120? Wow, this is like you guys have some insane like listing down speed. Yeah, I guess everybody seems to know this already. Can somebody just one of you just tell me how this 120 comes?
Like we took five places for the five numbers. Then for the first place,
Yeah,
we have five choices of numbers, and
yeah.
uh, then we will use one number, and it will left four numbers. Then we have four numbers left. Then gradually 3, 2, 1,
Yes.
and then 5 times 3 times 2 times, that's 120.
Yes. Okay, that does seem to be the idea, right? So the first digit, you have five options. You can either have 1, 2, 3, 4, or 5. The second digit, you cannot use the first digit again. So whatever you do, for each of these, you have four more options. Here you're going to have four more options. Here you're going to have four more options. Then for each of them, you're going to be branching into three more things because two things from earlier are cancelled out and so on. So you multiply all of these and then you get this 120. And okay, maybe like a question before we move on. Why do we not do 5 plus 4 plus 3 plus 2 plus 1? Why do we multiply? Just to make sure everybody's on board with the idea. Maybe somebody who's not Emon can answer this. Sorry, I didn't catch that.
Actually, this is derivable from the fundamental principle of counting. So I get this using that.
That's not a satisfactory answer. Like I asked, like why we do this and why we don't, and you're telling me it's because of the principle. Like okay, but like why? Why is the principle that way?
Oh,
Like why?
actually, in PNC there are two principles. एक होता है add करने का, when you have to take only one of them. But here we have to take, five digits
Hmm.
together. So we
Hmm.
use that thing of.
That's still not a very satisfactory answer. Uh,
Like
like,
we
do you see why it's not satisfactory?
Yeah, can I?
Like, you're just telling me it works because that's just how it's supposed to work. But like I'm asking why. Why is that how it's supposed to work? Huh, Shivam?
It because if we put any number out of the 5 in the first box, then whichever
Hmm.
in second we have many possibilities for number of possibilities for next all the four possible. So we can just see 5 plus 4 plus 3 plus 2 plus work. It we have matlab, the number possibilities when a number is on second place is same for all the four. So and we will have same 5 cases. So we do 5 into 4 and same for third, second and first place.
I think that's
I'm
maybe
not good
more
at
satisfactory.
explaining.
And your voice is cutting out, I think. I'm not sure if that was an issue with just, but yeah. The reason we are multiplying is because for each of these five cases, you are branching out into four more things. So for this you're going to have four things, for you're going to have four things, this 20. Now if it's in these 20 cases, you're branching out into things. So that's multiplying 3 because for each of the cases you have three more things and so on and so forth. So that's yes. You did a good. Okay. Okay. So that's it. So now we can generalize this and we can say, okay, if you were to look at in numbers, n digit numbers, let's say, using n different symbols and different, or maybe
Didi,
like, yeah,
your voice is
huh?
cutting. Your voice is,
It
poor
is?
quality.
Okay, okay.
Actually, we can't see your
Is it
video
better now?
clearly.
Wait, I think there is a network issue at your end. Like your video is paused and your voice is cracking.
Okay, okay, okay. Is it better now?
I think you should switch off the video so that like voice quality gets better.
Yeah, it's better now.
Okay, okay. Yeah, it should be.
No, actually,
It's
It's still not better.
it's not okay.
Didi, switch on your camera. We can't interact much. Feel like.
Yeah, yeah, yeah. You should also switch on your camera. I also want to interact. What is this? But can you hear me properly now?
Yes.
Yes.
Yeah. Now it's better.
Okay, that's good. That's good. Thanks for your patience. Okay. Yeah, it shouldn't go again. All right. Yeah, so we can now generalize this. Now, okay, instead of looking at, let's say, n digit numbers because we have finite, we have only 10 digits, we want to generalize it. So let's say you have n balls of n different colors. Then, or let's say we have n different colors. We have lots of balls of n different colors. Then what is the number of ways of arranging uh, n balls of all different colors This is one thing. And another question. So this is the question for without repetition, right? What if we allow repetition? So let's say mm, arrange m balls, but now repetition is allowed, like repetition allowed.
Like all balls are distinct.
Uh yeah, m different balls, but they could have two of them could have the same color.
Yeah.
That's allowed.
Okay.
So what is the first one again? For 5, the answer was 5 times 4 times 3 times 2 times 1. But 3, it was 3 times 2 times 1. For this, it's just going to be the first ball is you have n options. I think people have put their answers in the chat. I'll just explain. So you have n. The second one, then again you'll have n minus 1 options. The third one you'll have n minus 2, and so on and so forth until the last one only has one option. So this quantity, the product of all the numbers from 1 to n, is given a short form. It's called n factorial. It's like excited n factorial. Okay, and that's the answer for the first one. What is how do we solve the second one?
M to the power n.
Which way is it? Is it m to the power n or n to the power m?
Like you said, arranging m different balls and repetition is allowed. So m to the power m. Since there are m balls.
You have n colors. You have n colors, and you have lots of balls of n colors, and you want to arrange m balls. You want to have some m balls.
What? I can't hear you.
You have lots of balls. They come in n different colors, You want to find out how many lineups of M balls can you have. Does the question make sense?
Yeah, then it's like n different colors, now, so n to the power n.
Yes. So for the first ball, you're going to have n options. Second ball also you're going to have n options since repetition is allowed. Third also you're going to have n options and so on and so forth. So you're going to get m things since it gives you n to the power m. Does this make sense?
Yeah.
Yes.
Okay. Okay. Is there any question to anything about anything you've done? Gaurav, Shivam, Alex, Paras, Aishwarya, Tyasha, Imon, Gulshan, and
No,
everybody.
no questions.
Okay. Okay, then let's move on to something. Now let's say you have okay, let's say again you have uh m different objects. Or okay, let's try to give a story to that, yeah. Let's say there were m people who participated in an m people who participated in a OMC contest. And we are going to give a first prize, we are going to give a second prize, we are going to give a third prize, and we are going to give a fourth prize. So what is the number of different possible scenarios that could have happened? Like what how many different scenarios can occur in
There is no
this?
fifth, sixth, and seventh and on prize. Like there is no prize after first,
No,
right?
only the first four. No, if you get something after four, then like you don't get a prize. Boo-hoo.
So like there is MC4 if m is greater than equal to 4 and it's 0 otherwise.
No, I don't know what you're talking about.
No, you
Also, I
just
don't think it's entirely correct.
like just choose 4 of m to just give the prizes. And
Okay,
then
I see. Okay,
and
first of all, okay, we haven't we
the
haven't
win.
talked about choose yet, so I don't want any answers related to that. That's where I'm getting to. And okay, I see something in chat. People are saying m to the 4, right? Does everybody agree? M times m times m times m.
Like you can't give like one prize to two people. Like two prizes to one people.
Yes, so I should have clarified that. So all of these are like
Can
different
it
people. You
can it be
cannot give them. Hmm.
Then you can just do
can
like
it be
m
m
minus
times
1, m
m
minus
minus 1?
2.
Right. So one person can only get up to one prize. Up to one prize. We don't want to pamper anybody. Only one prize. So if this is the case, then the answer is
M minus 1, m minus 2, m minus 3.
yes.
If m is greater than 4, equal to 4.
If m is greater or equal to 4. Yes, that we should assume. Yes. Otherwise, this makes no sense. Okay. What if I want to generalize this even more? Let's say I want to give the first prize, the second prize, the third prize, the fourth prize, all the way up till the rth or the nth prize. Let's say I want to give out n prizes.
So you just total m
And the
minus 1.
important part here is that the first prize is different from the second prize. Like if I get the first prize, that's going to be different from me getting the second prize. Those two are different scenarios. That's the important part. So what happens if we do this? Yeah. If I want to generalize this to n, please don't annotate on the screen. Yeah. Let's assume n less than m.
So it's like just to get m minus 1 plus 1.
n
Yes, so
factorial
here
of
you had four prizes to give. So you had four brackets. If you're going to have n prizes to give, you are going to have n brackets. So you go up till what the first bracket is m minus 0, the second bracket is m minus 1, third bracket is m minus 2. So the nth bracket is m minus, what is it? M minus n plus 1. This is like a slightly scuffed way to write things. Instead, what I'll do is, okay, I will just multiply this by, I'll just go anyways till 1 and then divide by that number. So this is going to be my answer, but I'm going to multiply by m minus n minus 1 all the way up till 1, divide by m minus n minus 1 all the way up till 1. So now both the numerator and the denominator are in nice forms, both that we know. This is just, the numerator is m factorial, the denominator is m minus n factorial. Make sense?
Yes.
Yeah.
Okay.
This is just MPN.
Yes. So this is the nice or fancy way to write MPN, or like the permutations of n. So this when you want to choose n distinct objects with an ordering from m distinct objects or people. I'm not objectifying people. Sorry. Okay. Anyways, everybody on board with this? Any questions about any of this? Okay, I will take the silence as a no. All right. Now let's do something more interesting. Let's say that I don't want to give n distinct prices. I just want to choose n people and give them one chocolate, like the same chocolate. There's no different price for coming first. So I just want to see, I have m people and I just want to choose n and give them all the same price. Give them the same the
We can just
same
divide the
price.
expression you obtained by n factorial, since in that expression we counted each case in this n factorial times. So we just divide them together.
Yes. Exactly. Is there anybody who has not seen this before? Speak up. Okay.
Me.
You have not seen this. Okay, first of all, Gaurav, is this okay so far then? Gaurav Sharma, is this okay?
Actually, I did not understand, that thing. Like you have to give 4 prizes of OMC. Then how is that thing which you did possible? Right?
This, right? Okay.
Yeah.
Good. Yeah, you should speak up like at the moment you don't understand so that we don't like, go ahead and then like we have to come back. Like it's fine, like
Yeah.
nobody's yeah, okay. Okay, good that you asked. So you want to give 4 prices, right? And out of m people. So how many choices, let's say you want to first choose the first prize. How many options do you have for choosing the first, who to give the first prize to?
Like, if there are M people, we have M choices. Uh, I
Yeah, you
don't.
have m choices. Exactly. So you can either give first prize to the first person or the second person or the third person and so on until the mth person. Now you want to give a prize to the second person. How many options do you have for to choose the second person?
Oh, yeah, yeah. Thank you. I understood this thing. Now we can move forward.
Okay. Okay, good.
Yeah, thank you.
Yeah, don't hesitate to speak up at any point. Like I don't like like this class is for you to understand things. So if you're not understanding, then like that's like not like your issue. It's like a me issue. So I will explain again. Okay. So now the question is slightly different. What we want to do is we want to choose n people and give them the same price. So do you see how this question is different? First of all, like for example, if I would have chosen the first 4 people as 1, 2, 3, 4 here, or I could have chosen them as like 3, 2, 1, 4, and this is for the first prize, second prize, third prize, fourth prize. These both are counted different as different scenarios in this question. But now
Uh,
I'm saying ki both of these scenarios have to be counted as the same in this question. because there is no differentiation between anybody getting a first prize, somebody getting a second prize, and so on. Everybody is going to get the same small piece of chocolate. So do you understand that this is an entirely different question?
Yes, yes.
Okay.
Yes,
So
here
how do
prizes is
we?
same.
Yes, exactly. And now the thing is, okay, so how do we go about solving this?
Well, we just counted each case there in factorial times.
Right. So any scenario from here, consider any scenario from here where we are basically choosing n people and we are all giving them the same prize. If instead for each of these scenarios, there's going to be n factorial scenarios where you can, uh, first you choose these n people, and then once you've chosen them, then you can permute them in n factorial ways. So for each way of choosing n people and giving them all the same price, there's going to be n factorial different scenarios to give them all different prizes. Does that make sense?
Yeah.
So,
Yes.
yeah.
Yes, yes. I see. I see.
Yes. So whatever the answer for this question is, let's call it some x, then x times n factorial is just going to give us the number of permutations, which is basically the answer for the last
Yeah.
question, right?
Yeah.
So x is just going to be whatever our answer for the last question was, divided by n factorial.
So we are done.
And this is known as n choose r because you're just, oh sorry, not n choose r, m choose n, because you're just choosing n things and not permuting them in any way. Everybody on the same page? Ah, yes, yes, about the discussion on the chat. The last four lectures, they have not been put up, but I'll make sure to put them up. They have like been put up. There's because of some laziness from my side. So if it gets late, then just like feel free to ping me, or even Arnav. I will take this liberty to say that you should ping Arnav also for no reason. Don't ping a lot. I'm just saying if it's not been put up in a week, just remind me once and we'll make sure to put it. I'll put them up by today. Huh. Okay, was there some question? Why n factorial? Because we're dividing by n factorial, because for each of these scenarios, there are n factorial more scenarios where we can permute all of them. So you consider a scenario where you're just choosing and giving everybody one chocolate. So you already have n people. The way to get to the earlier scenario of everybody getting a different price would be to permute each of these scenarios, and there are n factorial ways of permuting each of these scenarios. So that's what you get. That's why the n factorial is coming. Does that make sense, or do you want me to take an example?
Better if
Nikhil.
you
Yeah.
take an example.
Okay. Okay. So let's consider, for example, let's say you have 1, 2, 3, 4, 5, and you want to choose three out of these. Or let's say you want to choose three out of these, right? So what are the different ways? Maybe just 1, 2, 3, 1, 2, 4, 1, 2, 5. And then you have 1, 3, 4, 1, 3, 5, and 1, 4, 5. And 2, 3, 4, 2, 3, 5, 2, 4, 5, 3, 4, 5. Right? These are all the ways of choosing three different things where the order doesn't matter, where everybody is getting one same chocolate. But what we can do is, now if we want to list down all the numbers, all the scenarios where it does matter, the first rank does get something different, the second rank does get something different. How will we list them down? How will you list them down? You can just take one scenario from here, this is 1, 2, 3, and list down all different permutations of this, right? So 1, 1, 2, 3, 1, 3, 2, 2 1 3 2 3 1 3 1 2 3 2 1. You can take this scenario and list down all the different permutations for that. You can take this scenario and list down all the permutations for that. So basically, the total number of different ways of choosing 3 so that the order does matter is just going to be whatever this number is multiplied by 6, because for every scenario of 6 more, 6 different scenarios. So for this, you're going to get 6 things here. This, you're going to get 6 things. This, you're going to get 6 things. So total number of permutations is, so 6 times the number of combinations is going to be the number of permutations. And this 6 here is coming from 3 factorial, because that's the number of ways of permuting 1, 2, 3. Does that make more sense, Nikhil and Gaurav?
Oh, yes, yes. Thank you.
Okay. How about Nikhil? What is the green column? Yeah, this is we were trying to solve 2 questions, right? One was when the order doesn't matter, and one was when the order does matter. So if you want to, uh, if you want to list down all the different scenarios in which the first rank gets a different, the second rank gets a different prize, and so on, then it's going to be. And how will you do it? First, you can just list down all the ways where it's all the where everybody's getting the same price, and then you can just list down all the permutations in each scenario. That's the green column is basically trying to answer the first question by answering the second question. This is actually a very important technique that pops up a lot maybe later in RMO type things also, which is called double counting. And you count the same thing in 2 ways. Yes, you count the same thing in 2 different ways and argue that since we are counting the same thing in 2 different ways, the 2 things must be equal. The 2 quantities must be equal. Okay. Let's try to solve another question. If is everybody on board? Okay, let's try to solve another question. Let's say some little little Arnav loves to play with switches. So his house has like a big switchboard where there's like 1, 2, 3, 4, 5, 6 switches. And what he likes to do is just like randomly go and switch some switches on and switch some switches off just for no reason. So now the question is, yeah, can somebody guess what the question I'm getting at is?
Number of different possible lights you can switch on.
Yeah. Yeah. So what is the number of different ways of like, thought, thought, thought.
2 to
Yeah.
the 6.
2 to the 6, yes. And why is that?
Because like each possible switch has 2 states. Either it can be off or it can be on.
Exactly.
So
The
you can-
first switch can either be on or it can be off. The second switch, it can either be on or it can be off. The third switch can either be on or off. And so on. Two, 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 two. And then because of multiplication principle, we multiply all of them. We get 2 to the 6. Yeah. It seems everybody's on board with this. Is everybody on board with this? Does this make sense?
Yes.
Okay. How about like Nikhil and Gaurav and other people who are like quiet? I don't know, Gulshan, Ashwarya, Alex, Dolendra.
Actually, this state like ki, how many switches Arnav will switch? Like he can switch two, three, or four. Like was it given in the question that he will switch on or off all the switches or something?
Yeah, that
So-
he like it depends on his mood. Like if he's feeling happy, then he'll switch on a lot of switches. If he's feeling sad, he'll switch off a lot of switches. So it's up to him. Like it's not fixed. The number of switches he'll keep on is not fixed.
Didi, I
oh,
have a question.
Yes, Shivam.
Can we also like proceed like if we switches 2, then we have 6 choose two possible ways. Like this 6 choose 0 plus 6 choose 1 till 6 choose 6.
Exactly. So we can also solve this question in another way by observing that okay, if he switches, let's say they're all initially off. That's one stage. So okay, O off and on both have, so I'll just say F. F means off and N means on. So initially, if all of them are off, then then that is there. Then you can have one switch on. How many ways are there where there is only one switch that is turned on? That's going to be 6 choose 1, right? Because you're choosing one switch to turn on. How many ways are there says that you can choose two switches to turn on? That's going to be 6 choose 2. How many ways are there says that you can choose three switches to turn on? That's going to be 6 choose 3. And so on and so forth until how many ways are there so that you can choose 6 switches to turn on? There's just one
Basically,
way.
6
Turn, yeah, and 6C0.
That's
So this is also another way of counting the same thing, right?
yep. So you get that sum of all NCRs to the N.
Yes, so you get that this is in fact has to be equal to 2 to the 6. Because we are answering the same question. So if you're answering the same question, you cannot have two different answers. So the two answers have to be the same. In fact, we can generalize this to by considering n switches. We have nc0 plus nc1 plus all the way up till ncn has to be equal to 2 to the n to consider n switches. So thanks to little Arnav for playing with the switches and teaching us a valuable lesson. Okay. Is Arnav here or no? I think he left. Oh, he is here. Okay. Anyways. So, right. Okay. Okay. Let's do some more things. There's like so many cool things you can do here. Let's try to list down all the things. Let's say you have mm, only one object. How many different ways? Okay, first of all, like nobody asked this question. What does choose zero even mean?
Choosing
Uh,
nothing.
Choosing
yes.
nothing.
Yes. So like should it and what is n choose zero equal to? Does it make sense
By
to choose
form
nothing?
It's
Hmm.
equal to
by
1.
formula it gives 1.
Okay, what is the formula? The formula is n factorial divided by 0 factorial into n factorial. Okay, but what is 0 factorial? Like, does 0 factorial make sense?
Well, it
It doesn't
actually
make sense, but it is 1.
It doesn't make sense, but you have to agree because Shivam has told you that it has to be 1.
it's just taken conventionally to be 1 so as to just like to make the formula valid for odd R.
Ah, just you put a gun to zero's head and be like, your factorial has to be 1. Otherwise it's going to be 4. Okay, another way I find like one way it is just like satisfying to look at as to why 0 factorial is 1 is observe that n factorial is just n minus 1 factorial into n, right? So then you can try to get 0 factorial from here. So you plug n as 1, you get 1 factorial has to be 0 factorial times 1. And for the world to be sane and not explode, you would want ideally 0 factorial to be equal to 1. So that's one like satisfying way to sort of convince yourself that okay, it makes sense for it to be 1.
Yeah, but
Uh,
what does n choose zero means?
What is
right.
this
What does n choose 0 even mean? Yeah.
canceling from both?
And choose 0 is just like you just choose nothing.
Oops, sorry, Shivam, your voice is breaking. I think you might want to check your internet connection once. Yeah, n choose 0 is basically you have n objects. How many different ways are there to choose 0 objects out of n?
That's obviously not one.
Yeah, just choose nothing. There's only one way to choose nothing. Just choose nothing. That's what it is. Another way you can try to look at that is okay. Can can somebody argue that n choose r the same as n choose n minus r?
Yes, because choosing R objects is equivalent to leaving N minus R objects behind. So there must be a bijection between them.
I love this. I love that you did not ask me to plug things into a formula and do it. Very nice. I'm happy. So you can just plug it into the formula and see that it works out. And that's all good. But uh there's a way to see it which says that if you want to choose R objects to keep, that's the same as choosing n minus R objects to throw out the window. So you can either just choose R objects directly or you can just choose n minus R objects and throw them out the window. Both of them are basically the same thing.
Yeah, that's clever
So
intuition.
this, yes. Okay, quite neat. So then another way you can sort of see is like n choose n is basically how many ways can you choose all n objects out of n? There's only one way. So the ways that is basically the same as choosing out 0 objects to throw away. So there's only one way you can do that. Just like don't choose anything. Maybe that makes somewhat sense. I don't know. Hmm. Or in this scenario of switches, it also makes sense, right? Because you want to choose 0 switches to turn them on, and there's only one way to do that. Just keep everything off. Choosing 6 from 10 and 4 from 10 is not the same. That's what Nikhil is saying. Ha ha ha, Saee Didi scammed you. 10 choose 6 and 10 choose 4 is not the same. Why? Can somebody tell why this is not the same?
Wait, isn't it the same? Like, how is it not the
I don't
same?
know. Nikhil is saying it's not the same. So the idea, Nikhil, is that if you want to choose 6 people from 10 to give a chocolate to, it's basically the same as choosing 4 people to not give a chocolate to. So they have to be the same thing. Oh, sorry, my OneNote has decided to randomly shut down. So give me a second. Actually, like more than a second. Um, it has restarted. Thank you for your patience. Okay. Okay, these two are the same quantity. Okay, let's do something. Any more discussion you want to? Anything more you have to say about any of this? I don't know. Okay. Uh, yeah. This there's like a lot of cool things you can do from here. For example, one way. Okay, let's list down a couple of things. When you have like some nice formulas and all, it's all good, but it's always good to look play with some numbers and try to find some patterns and stuff. So let's try to see. Let's say if you have only one object, how many ways can you choose 0 objects from one?
It's just like 1 to 0.
Yeah,
Don't
and
choose.
how many ways to choose one object from one?
Again, 1 way.
Okay, let's say now you have
One.
2
Okay.
objects. How many ways are there to choose 0 objects from 2?
Again, 1.
Okay, how about how many ways of choosing one object from 2?
2.
Yeah, you can either choose the first or the second. What about for how many ways to choose 2 objects?
Does again 1.
Yeah. How about for 3?
Yeah,
What
it's
is 3
1.
choose 0? Yeah.
then again 3, then again 3, then again 1.
Yeah.
And
How
then
about
constructing a Pascal triangle.
what happens for 4?
It's 1, 4, 6, 4, 1.
1, 4, 6, 4, 1. There's like a lot of cool things you can do here by just like looking at this triangle. Then, like, okay, first of all, what is even like the nice thing about this?
The sum of like thing is sum of the previous two things.
Yes. If you see, then anything over here is the sum of two things above it. It's like the famous Pascal's triangle. There's like a lot of so many cool things you can observe in this.
And then you just get that NCR is n minus 1 CR plus n minus 1 CR minus 1.
Right. So this, if you see, is just 5 choose 0, 1, 2, 3. This is 5 choose 3. This is 4 choose 2 and 4 choose 3. So the observation is that 5 choose 3 is somehow equal to 4 choose 2 plus 4 choose 3. Okay, also like a quick sanity check. This triangle seems to be symmetric. And that makes sense, right? Why does it make sense for the triangle to be symmetric about
Because
this?
NCR is equal to n minus NCN minus R. So it has to be symmetric.
Yes, exactly. NCR is equal to NCN minus R, so it has to be symmetric. Anyways, and there seems to be this other pattern also, 4C2 plus 4C3. Then we can also generalize this by looking at the nth row and then looking at the rth number. So if you have NCR, it's going to be the sum of these two things. It's going to be n minus 1 CR and n minus 1 CR minus 1. So you get this Pascal's identity of this, that NCR is n minus 1 CR plus n minus 1 CR minus 1. So basically, you remember how we like made little learn of switch on and off the switches to sort of prove that NC0 plus NC1 up until NCN is to the n. It's something this has like a lot of names. It's called double counting, bijection, proof by story. I like proof by story the most. So maybe one exercise that you can work on later is try to come up with a proof by story for this one. You can obviously just plug it. We already have a formula. So you can do the infuriating thing of writing out the formula and doing all the algebra. But that is just like, bleh, why would you want to do that when you can just make little Arnav do things?
Little
Okay.
Arnav could like just turn on R switches. Suppose like his mother has guided him to just exactly turn on R lights so as to save electricity.
Mm-hmm.
And he chooses like whether he wants to do the first switch on the first switch or not. So if he like switches
Yes,
the first,
that is indeed the idea. That is indeed the idea. Yes. So I will not like I'll not I'll not give the like I won't explain it in detail. So like if you didn't get that, then you should come up with your own theory later. So okay, you didn't get why it should be symmetric. So why should it be symmetric? Because basically, what does it mean for something to be symmetric? Something from the left side has to be equal to the exact opposite thing from the right side. And that is true, right? Because NCR, something from here, which is like R steps from the left, is equal to NCN minus R. We know that already, which is also R steps from the right. That's why it makes sense for the triangle to be symmetric. Is is that uh is that satisfactory? I can't follow the chat. Can somebody tell me if this was a satisfactory explanation or not?
yes, she said okay.
Okay, thanks,
Yes.
Sanskar. Okay. Uh yeah. So this is something I'll leave it as an exercise if unless like Sanskar already spoiled it for you. But okay. Uh what were we doing? Yes, we were doing this. You guys have any more observations to make in this? Just like a quick sanity check again. If you add up the things, 1 plus 1 is 2. 1 plus 2 plus 1 is 4.
Like
1 plus 3 plus 3 plus 1. 8. So it does make sense. It's like 2 cubed. 14641 is 16. 2 to the 4.
so like we can just say that like in the rth row the things in order are the coefficients of x plus 1 to the r. Like if you expanded, the coefficients are exactly those in the Pascal triangle.
Okay. Okay, sure. So Sanskar is telling this like cool magic trick that happens. So we know a plus b raised to 1. Let's start with raised to 0, raised to 1. A plus b raised to 1 is a plus b. What is a plus b squared?
A squared plus 2ab plus b squared.
Damn. Fancy. What is a plus b cubed?
A squared plus 3a squared b plus 3ab squared plus b cubed.
It's a cube. Yeah, I said a squared. A plus 3
Yeah,
a squared b plus 3 ab squared plus b cube. Now what Sanskar is saying, these numbers that are coming up, they are not arbitrary. They are some special numbers that we have already seen here before. So for 4, it's going to be something like a to the 4 plus 4a cube b plus 6 a square b square plus 4ab cube. Magic. Plus plus what? B raised to 4. Sanskar is a magician. Dumb. Yes, that's simply the binomial theorem. Can you come up with a proof by story for this as well? There's a lot of different ways of proving it. You can convince
yes.
convince
I think I've
yourself
already
this
thought
is
of a
true.
story of a little Erna.
Okay, good. So this is known as the binomial theorem. There's different ways. Since you guys had an induction class, you can now try to prove it by induction. You can try to prove it by proof by story. Okay. That's all good exercises.
And if we like
Yeah.
set a
So
equal
we
10
can
and b equal 1, we'll just observe that these numbers are powers of 11.
Yes. If you set a equal to b equal to 1,
No, a
then
equal
you will
10 b
just
equal 1.
get this. Huh? A equal?
10 b equal 1, then you will get a power of 11. Like, okay, that's a nice power. You can pattern.
Sure. Yes. Yeah, so maybe you would have observed that these are all powers of 11. You have 11, 121. This is like 11 squared, 11 cube, and so on. That can also be proved. Okay. Okay.
and also
Hmm.
in in that square expansion we can also see that each part raised and coefficients
I am so sorry, Shivam. Your
are
voice
just
is cutting out a lot. Maybe you can put it in the
I
chat,
will
yeah? Yeah. You try changing your internet connection, maybe. That might help. Okay. Yeah. This is like a bunch of cool things. Let's try to solve something. Let's say if you have let's say you have a big let's say again more lowers of little Arnav. Little Arnav lives on a grid because that's such a nice place to live in, right? This is the grid he lives in. Also, like it's also nice to live on the corner of a grid, so that's where he lives. This is where he lives. And this is where us Saee's place is. And he wants to visit Saeedidi. So now he can only this is let's have an infinite grid, let's say for now. It's a very big grid. And because he's like I don't know, for whatever reason he only likes to travel on these lines. Maybe there's lava in the middle, yeah? So you're not allowed to go here. So now the question is, how many different ways can little Arnav can he reach Saee?
Aren't there infinitely many ways like he can just up, down, up, down, up, down, up, down, and then just
Yeah. Yeah, I was just scamming. Little Arnav can just do a lot of time pass and just keep going up, down, and then decide to go to say he can do like up, down as many times as he wants. Okay, that's not an interesting problem at all. We can make it more interesting by saying, let's say, we can make Arnav even more obnoxious. Let's say he only likes to go, this is like north, east, west, and south, right? He only likes to go east or north. He doesn't like to move towards west or south. So he can only go right or up, right? Is the question okay? He doesn't know either. Okay.
yes.
And there's like a very cool way to solve this. This seems like a very overwhelming question. Like there's so many things here. That doesn't seem too nice. Maybe we can sort of break it down. What if Arnav lives here and Sai lives like right next to Arnav? Then how many different paths are there for Arnav to go here?
There's one
Yeah,
path.
just one. How about if Sai lives here, then?
Then there's like one path again.
Yeah, here.
Then again one.
Yeah, so anywhere he wants to go on this line, there's only one way to go. How about if he wants to go here?
There's again one.
Yeah, these are all ones. What if he wants to go here now? How many paths are there for him to go here?
There's two ways. Like he can come from the immediate left or
Yeah,
immediate
yeah, you
right.
can go here or here. So there's two ways he can come to visit me. What about here?
It's three ways.
Three. What about here?
Four. No, three again.
Yeah, three. Here, there's four, five. This is a nice pattern. 6, 7, 8, 9, so on.
It's just
Then
the Pascal triangle tilted 45 degree.
yeah, that's quite neat. Oh my God, this Pascals is coming up like everywhere. Why is it coming up in like powers and now it's like been like Arnav visiting me and stuff. That is like insane. Like what? Okay. And this will be 6, 10. Maybe this helps you come up with a story for the Pascal's identity, yeah? There's another way to look at it. So let's say the grid is uh this has length m, this has length n. Arnav is here, and I'm here. So
So
what
you
is
have
the
to
answer going to be?
m plus ncm, since like you have to take m steps right and n steps are like above, and like you can just arrange them
Yes.
and choose the
Yes,
basis of the n.
exactly. So another way to see this is there's different ways. Every path that Arnav takes, you can classify it as whether he went east or like every step you can either write an east or a north according to where he went, right? And since I live m steps to the right of Arnav, he has to go east exactly m times. And since I live n steps above to the north of Arnav, he has to go north exactly n times. So basically, if we're listing down all the paths that Arnav takes, then they're all going to be of length m plus n, such that east occurs m times and north occurs n times. And that's the same way as saying, as first having m plus n different slots and choosing m of them to go east. But that's also the same as just choosing n of them to go north. So your answer is going to be m plus n, C, m.
This is another way of proving. NCRs and NCM answer.
Right. Yeah, Sanskar, since you know these things already, maybe you can, just wait for us to think and come up with the solution. Yeah? Is that okay?
Okay, okay.
Okay. Is this okay with everyone? Do you want to repeat any of this?
Didi, how did you wrote the last m plus n choose m? Won't
Yeah.
it be m choose m plus n?
Shivam, I'm sorry, your voice is cutting out a lot. I cannot make out what you're saying. But I heard you ask why is it m plus n choose m. So basically, can you hear me all right, by the way? Can you hear me okay?
Yes, and now is my voice audible?
Yeah, now it's better. Now it's better. Okay, so I'll just repeat once as to why it's m plus n choose m. So that's because you are let's consider a smaller example, right? Let's say we have something like this. So what is one path which leads Arnav to my place? It's you go east, 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 and then you go north, north. Or you can just go east, east, north, north, east, east. Right? So basically, if you list down all of these paths, what are they going to look like? They're going to look like a number of ways of arranging six letters, out of which four of them are easts and two of them are norths. Is that okay?
Yes.
And how do we calculate how many such things are there? Basically, you have six different slots, out of which you want to choose two of them to put a north inside of them. That's the number of such permutation arrangements, right? Does that make sense?
Yes, and my doubt starts from here only.
What is your doubt?
But please check the chat.
Acha, won't it be m plus n choose m plus m plus n choose n? Why will it be that? So why should it be 6 choose 2 plus 6 choose 4? You want to find out how many that's an excellent question. So let's try to see why it has to be 6 choose 2 and not 6 choose 2 plus 6 choose 4. You want to think of it as you have uh, six different slots, as I said earlier, and you want to choose two of the slots and just put an n in them. Once you've put an n in them, the remaining you automatically fill up with an e. So once you have chosen the n slots, the e slots are automatically chosen. So the only thing you need to do is choose the n slots, and that can be done in 6 choose 2 ways. That's why it's
I
just
get
6 choose 2. Okay, great questions, great questions. Okay. Okay, shall we move on to something else? Okay. Okay, now how about this? Let us say, hmm. Okay, have you guys heard of this problem before? Uh, you have a number n. Let's try to solve this, right? How many ways? Okay, let's maybe I'll start with some examples instead of let's say for one there's only one way to write one. For two you can either just write it as two or you can write it as one plus one. For three you can write it as three or you can write it as one plus two or you can write it as one plus one plus one. For four you can write it as four or you can write it as one plus three or you can write it as two plus two or you can write it as one plus one plus two or you can write it as 1 plus 1 plus 1 plus 1. Do you see what I'm getting at? I want to sort of see how many ways are there to break down a number. So 5, you can either write it as 5, 1 plus 4, 2 plus 3, 1 plus 1 plus 3, 1 plus 2 plus 2, or 1 plus 1 plus 1 plus 2, or 1 plus 1 plus 1 plus 1 plus 1. Number of ways of reaching a number in Pascal's triangle? I don't follow. What do you mean by that? Okay. Any ideas for how we can solve this?
Do the order of the numbers matter in the terms that are summed? Like 1 plus 2 is the same as 2 plus 1 or not?
No, I have not. I mean, yeah, they are the same. So 2 plus 1 and 1 plus 2, they're essentially the same, right? Why count them again?
Okay.
For 5, it's 16. No, it's definitely not 16. I've listed them out here. 1, 2, 3, 4, 5, 6, 7. There's only 7 ways. Have any of you seen this problem before? Yeah, we have done so many things already, right? Like surely it's this should come on, you can do it. Okay. Maybe we can try to simplify this problem, right? Maybe we can look at like okay, the way to write it as a sum of only one thing is just one. How many ways are there to write it as a sum of two things? How many is there to write it as a sum of three things and so on? So now let's try to answer this question. If you're given n and you want to write it as a sum of r numbers, how many ways are there to do that?
Well, that's like not solvable by elementary methods because like this is just like the number of ways of partitioning and like stars and bars doesn't work here obviously because you're just counting in the order of some index and different.
Yeah, so stars and bars is what I'm trying to get at. But yes, you're absolutely right. I was just kind of scamming you guys. There is no
Exactly.
known formula for this. This is called the number of ways of partitioning a number. So I think somebody mentioned this in chat earlier. So Ramanujan was working on this for quite a while and he came up with a pretty good approximation for this number. So in fact, this problem is really hard to solve. We will not be discussing it. I don't know how to do it. Um, so sorry to disappoint you. But we can move on to something that is slightly more approachable.
Did
Instead,
you
as
audible?
the first question that yeah. Yes, I can hear you.
Well,
It's still
isn't
breaking a lot
that
though.
problem same as number of ways reaching a number in Pascal's triangle?
What do you mean by that?
Like in Pascal's triangle, also the two sum of two numbers will give another next number in the row.
True. So you want
So
to
can we relate that problem to Pascal's triangle?
so how will you relate, let's say, like 2 plus 3, you can get 5. So how will that come in over here? I'm not entirely sure I follow. That's something to think about, yeah. Can we relate to Pascal triangle somehow? Let's try to answer a simpler version of this question that we can in fact solve. So the first question that Sanskar had asked is 1 plus 2 and 2 plus 1 considered the same? And I had said yes. So let's relax that condition and say that okay, let's say 1 plus 2 and 2 plus 1 are considered as two different scenarios. So you have n is equal to x1 plus x2 up till xr, and order does matter. Order does matter.
So like stars and bars.
So will every number be in Pascal's triangle? That's a great question. Can you try to answer that yourself? Maybe later, yeah. Let's I can't follow the chat. There's like always some sort of weird glitch in my chat which doesn't allow me to randomly follow the chat. So you should just, can somebody tell me if there's something important in the chat and I don't see it?
Someone is asking, will every number be in the Pascal triangle?
Yeah.
Which is like obvious because NC1 equal N is obviously there.
Yeah. Yes. Okay. That's great. Okay, so how do we go about solving this?
Like you can consider like there are N.
Wait, Sanskar, you've seen this already before, so I wouldn't want you to.
Okay.
No, again, if you're putting something in the chat, I am not able to follow chat.
Someone is asking, can X size be 0?
Can x size be 0? No, we are assuming x size greater equal 1. And yeah, the question is that how many ways are there to write n as a sum of r numbers? So that the order in which you are writing the r numbers matters. And the r numbers are positive, all greater equal 1. Okay, some people are saying n minus 1, choose r minus 1. Where do we get that number from? Then we have another candidate. Some people are saying it's n minus 1, c r minus 1. Some people are saying it's n plus r minus 1, c r minus 1. I don't know which of these is correct. So another way, like this is like a boring way to think about it, I feel. Maybe another way to think about the same question is you have n balls, you have r boxes. And you want to put these n balls into r boxes so that each box has at least one ball.
And n must be greater than r.
Yes, that is true. N is at least r. So how do we deal with this? This is like a very, very cool trick. Should I do people who have not seen this before, do you guys want to think about it, or should we start discussing?
Think.
Okay, maybe we can give it another minute or two. If you have any ideas, do speak up. Okay. Mm, let's think about some things. So maybe we can get you started on something. So imagine you place the pen balls in some. Oh yeah, it's also important that to note that these are identical. These end balls are identical. We have, or like ROMC kids, I will say ROMC kids. I said that each OMC kid gets at least one ball. And not balls, you will give out chocolates because that's better. Okay. So you imagine these balls are chocolates. And you want to give them out to our people. So earlier we have already solved the question of when these n balls are all distinct. That you've solved at the start of the class itself. When all these n chocolates are different, how many ways are there to give them away? Wait, have we solved that question? We have not solved that question. Okay, we will get to that later. Let's try this one first. IOQ mocks. Okay. So how do we do? What do we want to do is basically want to partition these in chocolates into our different ways. Like maybe like this all goes to the first person. This goes to the second. You put another bar here so that this goes to the third, and so on. Right? So how many bars will you need to put to partition it into our different things?
Didi, please repeat.
So if you put one bar, then that partitions these chocolates into like two different sets, right? If you put two bars, then it partitions the chocolates into three different sets. So how many bars do
Yes.
you need to put to partition it so that you can partition it into our different sets?
R minus 1.
Exactly. So you have n of these chocolates and r minus 1 of these bars are like ways to partition things. And where am I allowed to put the bars? Can I put a bar here? Can I put two bars over here? This is the idea that we're going to try. So think more along these lines. So you want to
Bars
put r
should not
minus 1 bars.
coincide.
Yes, they should not be in the same gap. So what are how many choices do we have to choose from to put where the bars go?
R plus 1.
R plus 1? How? Let's say we have 10
Like
chocolates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where are all the places that you can't place a bar? So you can either place it here, or you can place a bar here, or here, right? So how many places are there where you can put a bar?
10 minus 1.
Yes, exactly. 10 minus 1 because you can't put it anywhere outside. So you're going to have 10 minus 1
I
places. If you have n
I
chocolates,
calculated
then
outside case also.
so if you have n chocolates, then how many?
N minus 1.
Exactly. So you have n minus 1 places where you can put a bar to put a bar. But you only want to put r minus 1 bars. You want to choose
N minus
places for
1
r
choose
minus
R
1.
minus 1.
Exactly. So you get that the number of such ways to do this is n minus 1 choose r minus 1. Does this make sense? Yay.
Yes.
Good job. Okay, so this is also called as then you can just like replace the chocolate with stars. And you have stars and bars. So this is called stars and bars. It's also called sticks and stones if you consider this as like stones and sticks. Anyways, just like this method has a lot of different names, but
Balls and
yeah.
urns.
Huh?
Balls and urns.
Balls and
Urns. URN.
urns. Okay, that's a new one for me. Yeah, but yeah, there's a lot of different ways. I
And doesn't
again, huh? Why not
doesn't
n choose r minus 1? Yeah, because you only have, so if you had 10 chocolates, the different ways of where you can possibly be put a bar, there's how many different places you can either put it here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if you have 10 chocolates, you have 9 places to put a bar. So if you have n chocolates in total, you're going to have n minus 1 places to put a bar,
I have a question.
right? Yes.
But what if each xi is more than 2 or equal to 2?
Great question. So let's say we want to, here our constraint was that every xi has to be at least 1. What if we want to ensure that everybody gets at least 2 chocolates? Because who is happy with 1 chocolate? Not Temuraz is not happy with 1 chocolate. Everybody should get at least 2 chocolates. Yes. So how do we deal with this?
you subtract one from each xi and then you just
Yeah,
subtract.
again, Sanskar, I would say that maybe just wait it out and like let people think. Since you've seen these techniques before, I would encourage you to, let others think and come up with solutions on their own. Okay, so xi is at least 2. So the way to deal with this, how do we deal with this? Somebody who's not Sanskar. We already know how to deal with the case when xi is at least 1. Now we have this additional constraint of it being at least 2. We want everybody to get at least 2 chocolates. So what we can do is, okay, we can take all our kids, give each of them 1 chocolate. And then what will happen is, then you will have n minus r chocolates remaining. And now you can distribute these n minus r chocolates into them so that everybody gets at least 1.
And then again same.
Yeah. So that tells you the number of ways will be n minus r minus 1. Choose r minus 1. First, xi at least. Is that okay? Great question, by the way. Is this okay with everyone?
Yes.
Okay. Let me ask you a question on similar lines. Let's say, what if I allow the x's to be 0? It's fine if somebody doesn't get a chocolate. I know that's evil, but for the sake of the problem, let's allow that. How do we deal with that? So I see some answers in the chat. Like, why? I mean, maybe you're right, but why? Also, again, like as I said earlier, I would prefer if somebody who has not seen this earlier is speaking up.
N-1 choose R.
N-1 choose R, but why?
Like there are N chocolates, and we can also give, there can be N bars. N-1 choose same
No,
same
if we
concept,
are
but
giving it
now
out
we
to
can have,
our kids, then you always need to have R-1 bars, right? If you have R kids, then the number of bars is always R-1. That doesn't change. Just to think about something along the lines of reverse, the exact reverse idea of this. How did we deal with the xi at least 2 case? We gave everybody one chocolate and then just like solved it from there. Instead, now here what we can do is increase the number of chocolates by some amount, give everybody, distribute the chocolates in everybody's side, everybody gets at least one chocolate, and take away one chocolate from everybody. So now people can have 0 chocolates. Like the condition for which we know how to solve the question is xi at least 1, right? Then how do we go from there to at least 0? Just take away one chocolate from everybody so that xi will be at least 0. Does the idea make sense?
yes.
So instead what we do is we start off with n plus r chocolates, distribute the chocolates in everybody so that that can be done in n plus r minus 1 cr minus 1 ways. And then take away one chocolate from everybody. So now that will ensure that means that you will have n chocolate, everybody will have n chocolates in total amongst them. That's why this plus r is coming from there, because we take one chocolate away from everybody and there are r people. So you will need r chocolates, r extra chocolates to begin with. So that's how you get n plus r minus 1, choose r minus 1. If you're allowed to have at least 0. Okay, maybe an interesting question, I will put this in the preset as well, is what if you have an sorry, the cat distracted me. I was saying ki now let's say you want to find out, you has given n, and you want to find out how many permutations of n are there, except the order does matter now. So for 5 you will have 5, 4 and 1 and 1 and 4 are considered different. 2 and 3 and 3 and 2 are considered different, and so on and so forth. So how many total such things will we have? And there's some nice things that come up. You will in fact get, let's try to quickly do it for 4 and see the magic. So it's like 4, you'll have 4, 1 plus 3, 3 plus 1, 2 plus 2, or 1 plus 1 plus 2, 1 plus 2 plus 1, 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. That's 1, 2, 3, 4, 5, 6, 7, 8. So for 4, you seem to get 8. And for 3, if you list down 1 plus 2, 2 plus 1, 1 plus 1 plus 1, you get 4. So that there seems to be some pattern. Maybe you can try to guess it and then try to also show that as to why that holds true. That's a nice exercise. Anyways, this was most of the things I wanted to talk about today. If you guys have anything more to discuss, we can do that for some or any more observations you know in this that are cool to explore, or any questions or doubts about anything that you didn't follow. Yeah. Okay. Okay, then I thanks for joining in and making this fun. This was very fun for me. I hope you learned something new and you also had fun.
Thank you.
Thank you. Bye bye. Source to learn more about this, uh, introduction and exploration of Olympiad combinatorics by Russell Mathur. Okay, I'll stop the recording and wait, how do I? Oh yeah.